In this video, I will be deriving an equation for the heat transfer rate inside of a co-current heat exchanger, which I've drawn a picture behind me. I'm going to go ahead and explain it a little bit and then get started with the derivation. So for this heat exchanger, it's basically just two concentric pipes, one on the inside, one on the outside. In my picture, I've only drawn about half of it. So if you want to kind of think about the circles kind of coming all the way back around, it's just two concentric pipes. And so for a co-current one, both of the flows are in the same direction. And so we have the heat capacity rate, which I'll explain in a second, and the temperature of the hot stream. It goes in and passes through a certain amount of differential area. And in that area, there's a small amount of heat transferred across this differential distance. And then the stream leaves the area. The hot stream leaves slightly colder. The cold stream leaves slightly warmer. And so here I've kind of graphed out what the temperature profile looks like. So for the hot stream, which is the top curve, it starts hot, and as it passes through the heat exchanger, it's going to cool down. And then the opposite happens with the cold stream. So it's going to start cold and warm up as it passes down the heat exchanger. So to go ahead and get started with our derivation, I'm going to go ahead and define two equations for our small amount of heat transferred. So the first one is going to be for the cold stream, and it's just going to be it's going to be for the hot stream. Since it's decreasing in temperature, we have a negative sign, and it's going to be the mass flow rate for the hot stream times the specific heat capacity for the hot stream times the differential change in temperature of the hot stream. And then we can go ahead and do the same thing for the cold stream. Both of these DQs are equal because they're just equal and opposite. So there's no negative sign for this one, so it's just the mass flow rate of the cold stream times the specific heat capacity of the cold stream times the differential change in temperature of the cold stream. So now, like I said, I'm going to go ahead and define the heat capacity rate, which is big C. And so all that is it's just the mass transfer rate multiplied by the heat capacity. So we can go ahead and rewrite these equations using that term. And so our equation for the hot stream just becomes a negative heat capacity rate of the hot stream times the differential change in temperature of the hot stream. And then for our cold stream, it's just the heat capacity rate of the cold stream times the differential temperature change of our cold stream. So now we have two equations for the small amount of heat added. We can also go ahead and define a third one in terms of the area. And what that's going to look like is it's going to be U, which is the overall heat transfer coefficient, times our change in temperature, delta T, times the differential change in area. So now that we have these three equations down, we can kind of get started with the derivation. I'm going to start by just expanding out the temperature change. So delta T can just be defined as the hot stream minus the temperature of the cold stream. And then if we go ahead and take the derivative of this, we're able to plug in some of our equations that we wrote down earlier. So we'll take the derivative of it. We get the differential change of the temperature difference equals the differential change in temperature of the hot stream minus the differential change in the cold stream. And we can go ahead and make those substitutions. So what that's going to look like is for the hot stream term, we're going to have negative dq over the specific or the heat capacity rate of the hot stream minus dq over the specific capacity rate of the cold stream. And this is still equal to our differential change in the temperature difference. So from here, I can go ahead and factor out the small amount of heat added, dQ. And now we can go ahead and plug in our third equation for the small amount of heat transferred. And we'll be able to separate out variables and take integrals of both sides. So just to kind of directly substitute this in, I'm going to have negative u times delta t times dA times 1 over c sub h times, or plus 1 over c sub c. So I just kind of directly substituted this in. And now from here, I'm actually going to give myself a little bit more room and start back up at the top. And so from this step, like I said, I'm going to divide delta t over. So for the left side of our equation, we have the derivative of the change in temperature over the change in temperature. And then this is going to be equal to negative u times our 1 over the heat capacity rates for both the hot and cold streams, and then we have dA left. So now we can go ahead and take the integral of both sides. And for our coefficients of integration, I'm going to go ahead and define this point as 1 and the outlet point as 2. And that's kind of how it shows up in the graph that I've drawn as well. So we're going to integrate from 1 to 2 for both of these integrals. And so for the left side, it just becomes a natural log of delta t sub 2 over our delta t1, which, as you can see, these values correspond to values on our graph. And so then for the right side, we still have our constants out front. And then the integral of the area just gives us A. So now from here, we have an equation, but we still have not yet incorporated the heat transfer rate, and that is what we want to get this equation in terms of. So I'm going to go ahead and define the heat transfer rate, which is just Q, and it's going to equal the mass flow rate. This is for the hot stream, times the specific heat capacity of the hot stream times the change in temperature. So in this case, we can rewrite the change in temperature as the difference between the temperature of the hot stream at the inlet point minus the temperature of the hot stream at the outlet point. And then we can go ahead and do the same thing and define Q for the cold stream, which is just going to be the mass flow rate for the cold stream times the specific heat capacity for the cold stream. And then in this case, the temperature change is between the outlet minus the inlet temperature. And so now that we have these two, we can go ahead and rewrite them using the heat capacity rate. Which just gives us the heat capacity rate of the hot stream up here and the heat capacity rate of the cold stream down here. And then we can go ahead and substitute these values in for our terms in our equation. So we just have to rearrange these for 1 over c sub h and 1 over c sub c. and then plug them in. So in doing that, we get 1 over the heat capacity rate of the hot stream. That's going to be equal to the temperature of the hot stream at the inlet minus the temperature of the hot stream at the outlet over Q. And then it is just the exact same thing for the cold stream. So now we can go ahead and make these substitutions. So I went ahead and factored out the 1 over Q since it's going to appear in both these terms. And so in our parentheses, we're just left with the temperature of the hot stream at the inlet minus the temperature of the hot stream at the outlet plus the temperature of the cold stream at the outlet minus the temperature of the cold stream at the inlet. And so from here, I can go ahead and rearrange the right side of this equation. I'm just going to go ahead and write it in the middle to give myself some more room. So if we arrange what's in the parentheses to correlate the outlet temperatures and the inlet temperatures, it's going to give us the temperature of the hot stream at the inlet minus the temperature of the cold stream at the inlet minus the temperature of the hot stream at the outlet minus the temperature of the cold stream at the outlet. And we can go ahead and now rewrite these two terms in here as this is delta T1 and this is delta T2. So that cleans up our expression quite a bit. So again, I need more room on the whiteboard. And so from here, we can go ahead and rewrite this with delta T1 and delta T2, and then we'll be able to solve for Q. So the equation then looks like this once we plug those values in. And now what's left is just to solve for Q. And so what that looks like is it's going to be U times A. I'm going to get rid of the negative sign and flip these. So now it's the delta T2 minus delta T1 over the natural log of delta T2 divided by delta T1. And so this is actually the equation for the heat transfer rate for this co-current heat exchanger. But we can actually go one step further. Most engineering firms and engineering textbooks write this expression out here. They call it the log mean temperature difference. And so in our textbook that we use for this class, it is expressed as delta TLM for the log mean temperature difference. And so our final equation just becomes this. And so it is the overall heat transfer coefficient times the area times the log mean temperature difference. And so this equation, since we did it all in terms of the temperature difference and not in outlet and inlet, it can actually be applied to countercurrent heat exchangers where the two flows are in opposite directions instead of the same direction.